Hello everyone, so we are continuing with number 2. Yesterday I covered number 1, and if you haven't checked it out, it's my YouTube channel. And today we're gonna go over number 2. The chemical reaction between the maleic acid and sodium bicarbonate occurs in the presence of water to produce the carbon dioxide and sodium malate. Okay, so they are just describing what the balanced reaction will look like. A student combines the mass of the maleic acid chunk and the sodium bicarbonate chunks with a sufficient water at 20 Celsius. So we'll write down that the temperature equals 20 Celsius. And the student determines that 0.0114 moles of carbon dioxide is produced after the reaction goes to completion. So we don't have really any equilibrium here since it goes to the completion. We have N, we're given N, we are given temperature. We need to find the number of grams of carbon dioxide produced. So for that, we just need to use the molar mass and multiply that with the number of moles. So let's start with that. The N of carbon dioxide, number of grams. So we need to find the mass of carbon dioxide is the moles, 0.0114 moles of carbon dioxide with the molar mass. Now, you can always use your periodic table, and carbon has 12.01 gram per mole and oxygen is 16, but there are 2 of them. So you multiply that by 2 and you should get 44.01. So you're gonna put the 44.01 gram on top and you put the 1 moles of carbon dioxide on the bottom. And we can cancel out the moles of carbon dioxide and then multiply these 2 numbers. 0.0114 times 44.01 gives me 0.501714. However, we are given 3 sig big here, and this is infinite number of sig big. So if you go with a 3 sig big, we need to round to the nearest thousandths place. Our 10,000th place is 5 or higher, so we need to round it up. So 0.502 grams of carbon dioxide will be the correct answer. Part B, part A, second part, is asking us carbon dioxide produced from the reaction at 20 Celsius was collected and found to have a pressure of 1.25 ppm. Okay, so it looks like we are adding more criteria here. Pressure equals, pressure of carbon dioxide equals 1.25 atm. When you see this and they ask for volume, you should immediately recognize the ideal gas law. PV equals nRT. So we start with that. We're looking for the volume of carbon dioxide, so let's divide both sides by the P, pressure of carbon dioxide. You can cancel that out. Volume of carbon dioxide is equal to N of carbon dioxide, R temperature over pressure. We already found, we're given the number of moles of carbon dioxide produced from the direction. 0.0114 mole, and the R is given in on the formula sheet. I think they use a 0.0821 or 0.0206, whatever is given. I'll just go use the 0.08206 liter atm per mole K, and the temperature has to be in Kelvin. Again, unless it's like a delta T, well, Kelvin and Celsius is not going to make any difference. If it's just T, you must write this in Kelvin, absolute temperature. So you need to convert it to Kelvin by adding 273.15. So if you add 273.15, you get 293.15 Kelvin. So we're going to use that. 293.15 Kelvin. And all divided by the pressure 1.25 atm. You can check the units, cancel, Kelvins cancel, moles cancel, atm cancel, and we are left with our desired unit, liter for volume. So 0.0114 times 0.08206 times 293.15, all divided by 1.25, you're gonna get 0.219389. Okay, so you don't want to write that many decimal for your final answer. So we gotta check our sig peak. So I have a 3 sig peak here from the mole. This is actually an infinite number of moles. An infinite number of sig peak. If it's a what was the temperature? 20 Celsius, 20.0. We might have 4 sig peak here. Yeah, we have 3 sig peak here. So we need to keep 3 sig peak, because you always want to go with the least number of sig peak when you multiply or divide. So I'm going to draw a line here. We have 1, 2, 3. And our 10,000th place is not 5 or higher, so we need to round it down. So your answer should be 0.219 liter of carbon dioxide. Okay, that's your answer. Let's go to part B. The student performs a second experiment that's identical to the first, except that the student grinds chunks of the malic acid and sodium bicarbonate into powder before combining the powder with water. So you may have learned this in biology class, like surface area to volume ratio. Though even if you have same volume, if you slice it or grind it, you make more surface area. And this higher surface area to volume ratio in chemistry can speed up the reaction. Okay, there's like 5 or 6 ways to speed up the chemical reaction, including like a catalyst or adding more solute. So, because you have more area in contact with water, you have more powder that are in contact with water, so the rate will go faster. So, if you grind it, okay, answering this question, if you grind it, the surface area will increase. So we just need to say the surface area of, what was it, the powder of the reactant will increase when the student grinds or pulverize the chunk. They didn't ask for the justification, but yeah, you should know. Alright, so part 2. The rate determining step for overall reaction is dissolving the solid. Will the time required for dissolving the solids in the second experiment be longer, shorter, or actually, this is like a justification of part A. So, yeah, same as the time required for the first experiment. In the first experiment, justify your answer based on the collision between particles. So you may want to pay attention to this collision theory, collision between the particle. Okay. Well, the short answer is it was shorter. Okay, so we can say the time required for the dissolving the solids in the second experiment will be shorter because we have more surface area, because the reactants have more surface area in contact with water. And cause more collision between water and the solid reactant. Therefore, it takes less time. Should be something along like this. Okay, I don't know if it's if we need to write this long, but yeah. They give you enough line, so just be consistent with your thought process and write it down. And I think they favor more like a how should I say it? They probably want a full sentence. And also you might wanna box like keywords that they, you can kind of save their time. Although I'm pretty sure they will read them all. Just easier for the graders to grade. Okay, anyway, let's move on to part 3. Now, when the reaction is complete, will the volume of carbon dioxide at the end of the second experiment be greater, less than, or equal to the volume? Now, thing is, they didn't say any altered conditions of temperature, pressure, or those ideal gas law conditions. In earlier step, pulverizing or powder definitely sped up the reaction. However, because all the original amount will be present, and we're not altering any amount of the reactant or the temperature, so it should stay the same. Okay, so part 3, when the reaction is complete, the volume of carbon dioxide at the end of the second experiment will be same as that of carbon dioxide at the end of the first. Because all the conditions such as pressure, temperature, as well as the amount of reactants, stay the same, while the second experiment favor the faster reaction, that is kinetics, it won't affect the thermodynamics. Okay, so you guys remember like the something like a catalyst. So the thermodynamics aspect would be like, you know, this change in temperature or change in energy won't change between unless you change some conditions of the beginning of the chemical reactions. So it has same theme here. Okay, so in other words, unless you change the amount of reactants in the second experiment, or change the temperature, or change the other criteria, the volume of carbon dioxide will not change. Okay. All right, so let's move on to the next one. The student conducts an additional trial of the experiment and produce the following data table. We have a trial 3 and trial 4. So part C is asking us to find the limiting reactant. Based on students' data, identify the limiting reactant in trial 3. So trial 3. Okay, if you go back to the original equation, we have 2 reactants. Okay, we have this. Actually, we have in table maleic acid and sodium bicarbonate. Maleic acid and sodium bicarbonate. Okay, those are the 2 reactants, and we need to convert this to product, the carbon dioxide. So this can be done by stoichiometry. So I'm gonna start with the first one, the maleic acid. We have 1.543 grams of H2C4H2O4 times, okay, we need the molar mass of this. Now the molar mass of this hydrogen, there's 4 hydrogen here, 4 times 1.008. Again, you can always look up your periodic table. And we have a carbon that's 12.01 times 4. Okay. And then we have 4 oxygen. Everything is 4, 4, 4. Yes, we're gonna get 116.072. Now where do I put that? On the bottom. So 116.072 grams of H2C4H2O4. So we can cancel out the undesired unit, and we have 1 moles of maleic acid. Now we still need to pay attention to the coefficient. If you go back here, the coefficient is 1 to 2. So we don't have to worry much, because if you do just 1 mole of the maleic acid, 1 mole of that is going to create 2 moles of carbon dioxide product. Okay, so we're gonna compare that and see which one is smaller. So 1.543 divided by the molar mass, and then multiply that by 2, and you get 0.02658. I'm going to keep 4 sig big, 6. So I'm going to get 0.02659 moles of carbon dioxide. Let's look at the other reactant, sodium bicarbonate. So we're given 1.251 gram. 1.251 grams of sodium bicarbonate. And as usual, we can find out the molar mass. 22.99 plus 1.008 plus 3 oxygen. And when you put that in, you're gonna get like roughly 72. Excuse me. Turns out I forgot. Wait, I think I forgot something. 22.99 plus 1.008 plus, oh, I forgot carbon. Okay. So plus 12.01 you're gonna get 84.008 grams of sodium bicarbonate for 1 moles of sodium bicarbonate. Okay, then we cancel out the grams. Now this is tricky unless you paid attention to the balanced chemical reaction. In the moles of reaction, we need to consume 2 moles of sodium bicarbonate to make 2 moles of carbon dioxide. So if you do this right, you're gonna need to put 2 moles of sodium bicarbonate. Again, that's all from the coefficient of the balanced chemical reaction. And it's giving us 2 moles of carbon dioxide. And we cancel out the undesired unit. And then we're gonna compare which one is smaller. So 1.251 divided by 84.008 times, well, 2's cancel. So that should be it. I got 0.01489146 big. So let's just truncate it here. So you get 0.01489 moles of carbon dioxide. So we're gonna make a verdict here. So we're gonna say the limiting reactant or limiting reagent is sodium bicarbonate because the amount carbon dioxide produced is smaller in theoretical yield. Okay, it's smaller. Okay, so that's how you answer the limiting reactant question. Where was it? Part C. And then part D, if you need to elaborate more, I think this is enough. Yeah, College Board, I think, is wrote like this. You can also say how, because it gives a less yield, that this reactant will get used up faster before the other reactant get used up, all used up. So, I think this is okay. So I'm just gonna move on. Part D, the reaction has a value delta S naught greater than 0. So they tell us that delta S naught is greater than 0. So this is change of entropy. The standard state. The higher the entropy, higher the change of entropy, the more chaos, the more orientations or more spatial arrangements you can make for any given reactant. So yeah, so using the particle level reasoning, explain why the entropy increases as the reaction progresses. Okay, so for that we need to look at the balanced reaction. So if you look here, we have we start with the both aqueous state, and then we end up getting the gas. And not only that, we do get more moles, but College Board doesn't seem to care about that. Yeah, we start with the 3 moles and then end up getting 5 moles. I think that should be okay to include, but the main answer, what they really ask is for you to recognize the gaseous state has more chaos or more spatial order or spatial arrangement of chemicals in the given volume. Because gas have higher kinetic energy, and that means they can move around faster and also occupy more different spatial arrangement than something that's aqueous. I mean, aqueous, once they're dissolved, yeah, they can really, make a lot of different arrangement. But compared to gas, they have definitely lower kinetic energy, and their movement being liquid is definitely in liquid is limited compared to gas. So we're gonna have to answer it that way. So I am going to say, okay, the reactant has or reactants are all aqueous. Aqueous state in water with limited movement and spatial orientation. On the other hand, the product, such as carbon dioxide or 2 moles of carbon dioxide, are gases which has more kinetic energy and cause more spatial arrangement. Alright, I'm trying to write fast so my video is shorter, but at the sacrifice of writing here. Spatial arrangement and more dispersal that favor chaos and higher entropy. So because the product is higher, than the reactant, we'll get overall positive. Yeah, so let me see if I answer the question. So this was, yeah. So we'll say the entropy increases. Okay, I'm gonna move on. Part E. The student noticed that the temperature of the reaction mixture decreases as the reaction takes place and correctly determined that the reaction is endothermic. So if it's endothermic, we're talking about delta H naught is positive. Okay, it's a positive. Student claims that the reaction is thermodynamically favorable at all temperature because delta S naught is greater than 0. Okay, that was true from the last question. And the reaction is endothermic. Do you agree or disagree with the student's claim? Okay, for us to determine this, you need to pull out the Gibbs free energy in terms of the enthalpy and entropy and the absolute value temperature. So delta G naught is of reaction is delta H naught of reaction minus T delta S naught reaction. Okay. We know that this is positive and we have minus, and delta T here is absolute value temperature, so this is always positive. And it's true based on the balanced chemical equation that we saw, the delta S naught is also positive. Now the thing is, I have to disagree with the students because the students said under all temperature, it will be thermodynamically favorable. You need to describe that it depends. you can either say delta T delta S naught, the magnitude of this has to be greater than delta S naught reaction, or delta G naught reaction to be negative, which is thermodynamically favorable. Okay, again, delta G naught has to be negative for the reaction to occur spontaneously. So that's one way. Another way, you can also refute the student's claim by saying if it's under all temperature, like all temperature, under all temperature that the reaction becomes favorable, delta H naught has to be the exothermic, but it's not. If you describe it as exothermic, then yes, student will be correct, but endothermic is not. So you can also describe it that way. Alright, so we're gonna move on. The next question. The next student investigates the acid-base behavior of maleic acid. The student notes that the maleic acid is a diprotic acid. The two acid dissociation processes that occur are represented by the following equations. So it's a diprotic, so they're gonna like dissociate just like a sulfuric acid, or triprotic like phosphoric acid. So we'll have a multiple Ka values. Now remember the Ka1 is always greater than Ka2, and the Ka3, or the lower you go, then the dissociation gets way weaker. Alright, so calculate the pKa2, so meaning the second row here, value for this ion. Okay, pKa is simply negative log, just like a pH. Just recap, pH equals negative log of concentration of H plus. pKa has the same nature. It's negative log of Ka value. So if you need to find the second one, Ka2, we look at the second row and just plug it in this Ka value. Negative log of 8.5 times 10 to the power of negative 7. When you put this in your calculator, the sig has funny row here. So I got 6.07, so I'm gonna write just many decimal. However, we see a 2 sig here for pH or pKa. That 2 sig will be 2 decimals. So we don't round it up as 6.1. We just answer our question as 6.07. Yes, you have 2 sig here, and it looks like we got 3 sig. But again, when you convert the Ka, or the concentration of hydrogen, to pH or pKa, that number of sig will become number of decimal. So it's 6.07. And last one, G. The buffer solution with a pH of 7.0 is prepared. So we're given pH of 7.0 is prepared using this guy here, completely deprotonated, and then this guy here. So in other words, we already know pKa2. What was it? 6.07. And then you see that ratio. The moment you see this, you should immediately recognize you just need to pull out the Henderson Hasselbalch equation. So let's pull that out. pH equals pKa plus log of the concentration, conjugate base concentration, and the acid. Alright, so we need to find the highlighted region. So this is more of a math question. I'm gonna plug it in 7.0 for pH and pKa 6.07, and then we get log of all this. The first thing, we gotta subtract 6.07 on both sides. And we get 0.93 equals log of this junk. Okay, how do I get rid of log? You need to put the inverse of log, which should be power of 10. This is common logarithm where there's a implied 10 base. So this way you cancel this out, and the ratio of this concentration can be calculated using a calculator. So C4H2O42 minus over HC4H2O4 minus is 10 to the power of that, giving us 8.5113. Okay, so when you go from pH to something like the exponent, now that 2 sig big, we see the 2 sig big here, 2 decimals, and that will be a 2 sig big. So you truncate everything after the 10th place. So the ratio is 8.5. Okay, 8.5 is the answer to G. Alright, thank you very much for watching my long video here. I'm not sure if I can make number 3 by tomorrow, but again, I'll try my best whenever I have time. Alright, until next time, thank you very much.